Welcome back to the deep dive. We have let's say, a massive stack of documentation on the virtual table today. And I think this one is really going to resonate with anyone who has ever, well, lost sleep over network security.
Oh, for sure.
We are looking at the absolute backbone of Azure networking, network security groups, or NSGs.
It's one of those topics that sounds a bit dry on the surface until you realize it's often the only thing standing between your sensitive database and the open internet.
Exactly.
Yeah.
And the scenario the source material points to kick this off is, it's a classic one. You've got a company, let's just call them Megacorp, and they have offices everywhere.
Right.
They finally decide it's time to migrate key systems to the cloud. But the C-suite is, well, they're paranoid. They're saying, we are not moving a single byte of data unless you can guarantee us absolute granular control over who touches our servers.
Which is a completely fair demand. I mean, if you're coming from an on-premise world, you're used to physical firewalls, locked server.
Air-gapped networks, all of that.
Yeah. Exactly. Moving to the cloud feels like moving into a glass house. You can see everything, but you feel so exposed.
So the mission for this deep dive is to figure out how we put the curtains up and, lock the doors. We're going to break down how NSGs function as the gatekeepers of the Azure Virtual Network. And for anyone listening who is currently grinding through study guides for the exam AZ-104, Microsoft Azure Administrator, perk up your ears. This is your bread and butter.
It really is. You cannot pass the Azure Administrator exam, and honestly, you can't run a secure cloud environment without a deep, almost intuitive understanding of NSGs. It's the foundational layer of defense.
Okay, so let's start at that foundational level. When we say network security group, what are we? What are we actually deploying? Because I think there's a misconception that it's a virtual appliance.
Right.
Like a digital box that sits on the wire.
That is a very common misconception. An NSG isn't a virtual firewall appliance that you spin up, wait for it to boot, and then, pay an hourly rate for. It's much more integrated than that.
It's a configuration resource?
It's a configuration resource. Think of it as a set of access control list ACLs that live in the Azure fabric itself.
So it's a filter that exists within the network plumbing.
Exactly. It's a filter. It is a list of rules that says traffic from A to B is allowed, or traffic from C to D is denied. It inspects traffic at the network layer, so layer 4 for the networking nerds out there.
Oh, okay.
It looks at the source, the destination, the port, and the protocol.
Famous 5-tuple?
The 5-tuple. Every single decision the NSG makes comes down to those 5 data points: source IP, source port, destination IP, destination port, and protocol. It just checks the packet header against your list, and if it matches, it executes the action. Allow or deny.
Okay, so we have this list of rules, the clipboard of authority, if you will. The next logical question is, where does the bouncer stand? The source material mentions 2 specific places where you can attach these rules, and this seems to be where the strategy really comes in.
Right. This is where you move from just configuring to architecting. You can attach an NSG to a subnet, or you can attach it to a network interface, which we usually just call an NIC.
And strictly speaking, you could do both, right? But help me understand the strategy. Why would I choose one over the other?
Okay, so if you attach an NSG to a subnet, you are applying those rules to every single resource that lives in that neighborhood. It's a broad stroke.
Like a gate for the whole community.
It's like putting a guard shack at the entrance to a gated community. You say, nobody enters this subnet on port 80. Boom, every VM inside is protected from port 80 traffic.
Which is efficient. You don't have to configure every single server individually.
Correct. It's great for broad policy enforcement. But then you have the NIC level. This is specific to a single virtual machine. If you attach an NSG here, you're engaging in what we call microsegmentation. You're locking down that specific front door.
So, playing devil's advocate here, if I have a subnet NSG, isn't adding an NIC NSG just?
Redundant. Yeah, people ask that all the time.
Exactly. Why do I need a guard at the front door if I have a guard at the main gate?
That is the core question of defense in depth. Imagine your subnet allows web traffic because, you have web servers there, but one specific server in that subnet is a backend processor that shouldn't receive web traffic.
I see.
The subnet NSG lets the traffic in the main gate, but the NIC NSG on that specific server stops it right at the door. It allows for exceptions and much tighter security within a group.
Okay. And the source material uses a term that I think we should unpack here, the DMZ, or screened subnet. It sounds very military, but it fits this logic, doesn't it?
It does. DMZ stands for Demilitarized Zone. In a traditional network, the DMZ is a buffer zone between the wild, dangerous internet and your safe internal network.
Okay.
In Azure, we build this using NSGs on a subnet. You create a subnet just for your web servers, that's your DMZ. You put an NSG on it that says allow traffic from the internet, but then on your internal database subnet, you have a different NSG that says block traffic from the internet.
So the DMZ subnet basically takes the hit, filters the traffic, and then passes only the good stuff deeper inside.
Precisely. It acts as that buffer.
Now, I want to get into the weeds of how these rules are actually processed, because I feel like this is where people get tripped up, where I've definitely made mistakes in labs. The sources talk about priority numbers.
Ah, yes. The priority number, the source of many, many troubleshooting headaches.
So my logic tells me that a higher number means higher priority. If I'm priority 1, I'm low on the totem pole. If I'm priority 1000, I'm the boss.
And in Azure, your logic would be wrong. You have to flip your brain. It's like golf scores lower is better.
So a rule with priority 100 beats a rule with priority 200.
Every single time. Rule processing starts at the lowest number, say 100, and works its way up. The moment traffic matches a rule, processing stops. It doesn't matter what Rule 200 says if Rule 100 has already made a decision.
Okay, so let's play that out. If I have Rule 100 that says block everything, and then Rule 200 that says allow web traffic.
Your web traffic is dead on arrival. The NSG hits Rule 100, sees block, and drops the packet into the digital void. It never even reads Rule 200.
That seems like a trap for the disorganized administrator. If you number your rules 1, 2, 3, 4, and then you realize you forgot something important that needs to go in the middle.
You're in deep trouble. I mean, you'd have to renumber everything manually. That's why the best practice, and you'll see this in every serious Azure environment, is to leave gaps.
Right.
Number your rules 100, 200, 300. Give yourself space to slide in a Rule 150 later without breaking the whole structure.
Future-proofing your own oversight. I like it. Now, speaking of rules we can't control, the documentation mentions default rules. These are the ghost rules that Azure puts in every NSG, whether you want them or not.
They're the safety net. You can't delete them, but they have very high priority numbers, around 65,000, so they're very weak. They only apply if you haven't written anything to override them.
There are 3 big ones mentioned, and I want to drill into them because one of them sounds pretty risky to me. Let's start with allow net and bound.
Right. This is critical to understand. By default, Azure assumes that everything inside your virtual network, your VNet, is friendly. This rule, allow net and bound at priority 65,000, allows any VM in the network to talk to any other VM on any port.
Wait, hold on. Isn't that a massive security risk? If a hacker compromises one server, say a web server exposed to the internet, can't they just use that permission to pivot to my database server?
You hit the nail on the head. That is what we call lateral movement. In a default state, Azure allows lateral movement everywhere within the VNet. In a zero-trust environment, or even just a reasonably secure one, you absolutely want to override this.
Okay.
You don't want your HR server talking to your R&D server just because they're in the same VNet. But out of the box, Azure allows it to ensure basic connectivity works so you aren't frustrated on day one.
Okay, that's a big takeaway. Don't trust the default intranetwork traffic. Then we have allow internet outbound.
Pretty self-explanatory. Your servers can reach out to the internet for updates, patches, downloading packages. Note that this allows the request to go out. The return traffic is statefully allowed back in. But this can also be a risk for data exfiltration, so high security environments often override this too.
And finally, the hammer. Denial and bound.
Priority 65,500. The end of the line. If traffic hasn't matched any of your custom rules, and it hasn't matched the VNet rule, it hits this wall and gets dropped. None shall pass.
Okay, I want to go back to that double jeopardy situation we touched on earlier.
Yeah.
The scenario where you have an NSG on the subnet and an NSG on the NIC. The source material says traffic has to pass both, but the order matters, right? This feels like a geometry problem.
It matters immensely for troubleshooting. You have to visualize the flow. Let's visualize a packet coming in from the internet inbound traffic. First, it hits the perimeter, the subnet NSG.
Okay.
If the subnet says no, the traffic stops right there. The VM never even knows someone knocked. If the subnet says yes, the packet goes through to the NIC NSG. Now, the NIC NSG gets a vote. If it says no, the packet is dropped.
So for inbound, you need 2 green lights. You have to pass the gate guard and the door guard.
Correct.
And for outbound, if my server is trying to send data out to the world...
It's the reverse. The traffic leaves the VM and hits the NIC NSG first. If that allows it, it travels up to the wire and hits the subnet NSG. If that allows it, it finally goes out to the world.
This is where I can see people getting confused.
Yeah.
I allowed it on the subnet. Why isn't it working? Well, Did you check the NIC?
Exactly. And there is a specific gotcha here that the source highlights regarding intra-subnet traffic. Traffic between neighbors. Since the subnet NSG applies to everyone in the subnet, you might think it doesn't filter traffic moving within that subnet, but it does.
So if VMA talks to VMB and they're both in the same web subnet.
The traffic leaves VMA. It hits the subnet NSG rules. If allowed, it enters the network. Then, as it tries to enter VMB, it hits the subnet NSG rules again because VMB is also behind that gate.
It's like having to show your ID to leave your bedroom and then show it again to enter the kitchen.
That's a great analogy. Generally, intra-subnet traffic is allowed by that default VNet rule we talked about. But if you start writing strict deny rules on the subnet, you can accidentally isolate servers from their neighbors and break your clusters.
This sounds like it could become a management nightmare very quickly, specifically managing IP addresses. If I'm building a rule that says, allow web servers to talk to database servers, do I have to list the IP addresses of every single web server?
In the old days, yes. And it was miserable. You have to remember, cloud infrastructure is dynamic. Servers spin up, they spin down, IPs change.
Right.
If you are managing security by updating a spreadsheet of IP addresses every time an autoscaler kicks in, you have already lost. You cannot scale security that way.
So what is the solution? The text introduces application security groups, or ASGs.
ASGs are the savior of the cloud admin. They allow you to abstract the IP address away entirely. Instead of defining who by an IT address, like 10.0.0.5, you define who by a label.
So I can just tag a server as a web server.
Exactly. You create an ASG object called web servers. You drop your VM network cards into that group. Now, when you write your NSG rule for the source, you don't type an IP. You select application security group, web servers.
That is so much cleaner.
It's dynamic. If your auto-scaling adds 50 new web servers tonight to handle Black Friday traffic, you just add them to the ASG. The security rule automatically applies to them. You don't touch the firewall rules.
The source provides a really solid example of this, an online retailer setup. I think walking through this logic step by step would really help cement the concept. Let's visualize it. We have a standard two-tier app. Tier 1 is web servers. Tier 2 is app servers that talk to a SQL database.
Right. So let's build the security policy for this using ASGs. We want the internet to see the web servers, but we don't want the internet to see the app servers. And we only want the web servers to talk to the app servers on a specific port.
Okay, let's write the rules. Rule number 1.
Priority 100. Source, internet, destination, ASG web servers, port 80 and 443, action. Allow. Now customers can see the website. Simple.
But the app servers are still dark to everyone, so we need rule number 2.
Priority 110. Source, ASG web servers, destination, ASG app servers, port 1433, that's the SQL port mentioned in the scenario, action, allow. Now the website can talk to the database backend.
And here is the zero trust part. What stops me from just bypassing the web server and connecting directly to the database from my laptop, or what stops a hacker who compromised a random server from scanning the app servers?
That's where rule number 3 comes in, priority 120, source, any, destination, ASG app servers, action, deny.
Wait, I need to pause you there. If I deny any, doesn't that block the web servers too? I mean, any includes everything.
This goes back to the golf score. Priority 110, allow web servers, is lower than priority 120, deny any. So if the traffic comes from a web server, it hits rule 110, gets a green light, and processing stops. It never even sees rule 120. If traffic comes from anywhere else, your laptop, a hacker, another server, it skips rule 110 because it doesn't match the source. It hits rule 120, matches any, and gets a red light.
That logic is elegant, but I can see how it's fragile. If you swap those priority numbers, if deny any was 100 and allow web was 110.
You break the application immediately. Deny any at 100 would catch the web servers first and block them. The prioritization is everything.
There's one other feature mentioned in the notes that fits in here, service tags. We talked about ASGs for our machines, but what if I need to allow traffic to, say, Azure SQL generally, or Azure Storage? I don't know the IP addresses of Microsoft's entire cloud.
And Microsoft doesn't want you to know them because they change constantly. That's what service tags are for. It's a label managed by Microsoft. You can write a rule that says, allow outbound to squile.east-to-us. Azure manages the thousands of IP addresses behind that tag. You just use the friendly name.
It's a huge time saver.
It is, compared to trying to whitelist IP ranges manually.
So we've built this complex web of subnets, NICs, priorities, defaults, ASGs, service tags. Frankly, my head is spinning a little. If I am an admin and I click connect and it times out, How on earth do I troubleshoot this? How do I know which rule killed my packet? Is it the subnet, the NAC, a default rule?
You can't just stare at the list. It's too complex to do in your head. You need a calculator. And Azure provides a tool literally called Effective Security Rules. You find it in the VM blade in the portal.
What does it actually do?
It does the math for you. It looks at the subnet NSG, looks at the NIC NSG, looks at the default rules, merges them all together based on priority, and spits out a single flattened list of here's what is actually happening.
That sounds like the absolute first place you should look when things break.
It is step one. Why can't I SSH? Check effective rules. Oh, look, there's a DNS SSH rule on the subnet that I forgot about. There is also Network Watcher, which has a failure called IP Flow Verify.
Oh, yeah.
That one is really cool. You literally simulate a packet. You say, if I send traffic from ITX to IPY on port 80, what would happen?
Yeah.
And Azure runs the simulation and tells you allowed or denied and points to the exact rule that made the decision.
That is incredibly powerful. It takes all the guesswork out of why is my app down?
It turns a 2-hour mystery into a 5-minute fix.
So as we wrap up this deep dive, let's distill this down. If our listeners are going to walk away with 3 key things to remember for their next architecture meeting or their exam, what are they?
First, respect the priority. Lower numbers win. Leave gaps in your numbering. Be kind to your future self who has to edit these rules.
Good advice.
Second, know the flow. Remember the gauntlet. Inbound traffic hits the subnet first, then the NIC. Outbound is the reverse. You have to pass every gate to get through. And third, move away from IPs. Use application security groups and service tags. Stop hard-coding IP addresses. It's just not scalable, and it's not secure in a cloud environment.
That brings us back to that initial scenario, the company wanting tight control. The source material ends with a really interesting, slightly provocative statement. It notes that if you create a virtual network and don't assign an NSG, traffic flows freely. The default state of a VNet is open.
That's right. Silence is acceptance.
So here is the thought to leave you with today. In the cloud is doing nothing the biggest risk of all. We spend so much time worrying about configuring the wrong rule, but is the real danger just assuming that someone else put the lock on the door?
Or, to flip the coin, is there a risk in over-engineering? We've seen environments so locked down with complex, conflicting rules that the business grinds to a halt and admins essentially DDoS themselves. The challenge is finding that sweet spot between Fort Knox and open for business.
That is the art of the Azure administrator. Thanks for breaking it down with us. Go check your effective security rules, everyone. We'll see you in the next deep dive.